somewhere beneath the surface of the Pacific Ocean, something enormous is moving. Not a storm, not a current you can feel from a boat or track from a shoreline. Something deeper than that, a pulse. A slow, continent-spanning surge of warm water traveling eastward along the equator, thousands of meters below the surface, carrying enough stored heat to reorganize the weather of an entire planet. Scientists have a name for it. They call it a Kelvin wave. And this particular Kelvin wave has been building for months, gathering force beneath the surface, while the world went about its business above. Satellites have caught it on camera, a bright thermal ridge pressing silently toward the South American coast. When it arrives, it will do what these waves have always done. It will uncork. And what comes out may be unlike anything recorded in the modern era. The El Niño Southern Oscillation has been running for at least 10,000 years, possibly longer. Its chemical fingerprints appear in ancient coral fossils. They show up in sediment cores drilled from ocean floors. Long before any human civilization kept written records, the Pacific Ocean was cycling through this same rhythm. This slow planetary breathing that shifts heat from the deep to the surface and back again, reorganizing rainfall across continents, lifting and dropping temperatures around the globe on a 2 to 7 year cycle that no single nation controls and no government can stop. For most of human history, that rhythm was simply part of the world, a natural heartbeat, sometimes disruptive, occasionally catastrophic, but familiar in the way that weather is familiar, something to prepare for and recover from, and ultimately outlast. That understanding is now being tested, because the Pacific is preparing to breathe again, harder than it has in decades. And the world it is about to exhale into is not the same world it has always breathed through before. The question that climate forecasters are struggling to answer in precise terms, and that this documentary is going to investigate, is deceptively simple. We know what a super El Niño does in normal conditions. We have the historical record. We have the damage estimates, the flood maps, the drought years, the billion-dollar agricultural failures. We know what these events cost. What we do not know, with any confidence, is what one of these events costs when it arrives on a planet that has already been running a fever for years. Start with the mechanism, because it matters. Under normal conditions, the tropical Pacific operates like a slow, enormous conveyor belt. Trade winds, the persistent easterly winds that blow across the equatorial Pacific, push warm surface water westward. They drive it from the coast of South America toward Asia and Australia, piling it up in the Western Basin. As that warm surface water moves away from South America, colder water rises from the deep to replace it in a process called upwelling. That cold, nutrient-rich water supports some of the richest fisheries on Earth. It also keeps the Eastern Pacific relatively cool. This is the baseline state, the Pacific at rest. El Niño begins when that baseline breaks down. The trade winds weaken. The warm water that had been held in the west by those winds begins to slosh back eastward. Sea surface temperatures in the central and eastern tropical Pacific begin to climb. And because the ocean and the atmosphere are in constant conversation, exchanging heat, moisture, and pressure, that shift does not stay in the Pacific. It propagates outward. The jet streams of both hemispheres begin to move. Rainfall patterns reorganize. Drought appears where there was rain. Floods arrive where there was drought. The shift cascades across continents and ocean basins and ultimately registers as a measurable increase in global average temperature, because the ocean is releasing heat it had been holding for years. This is El Niño. Not unusual, not alarming in itself. A 3 to 4 degree increase in sea surface temperatures in the right part of the Pacific, sustained for long enough, and the whole planet notices. What makes a super El Niño different is scale. At ordinary El Niño intensities, somewhere between 1 and 2 degrees Celsius above baseline, the disruption is serious but bounded. Specific regions get hit hard. Others barely register the change. But at super El Niño intensities, above 2 degrees, approaching 3, the volume of heat moving from ocean to atmosphere becomes large enough to physically displace both hemisphere jet streams simultaneously. The result is not a regional disruption. It is a planetary reorganization. Drought and flood, and wildfire and heat wave. At the same time, on multiple continents, thousands of kilometers from the Pacific itself. A disruption so large that the climate system as a whole has no undisturbed corner left to absorb it. There have been 4 confirmed super El Niño events since reliable records began. The events of 1982, 1991, 1997, and 2015. Each one left a mark that took years to erase. The 1997 to 1998 event alone triggered catastrophic wildfires across Indonesia, devastating floods along the Peruvian and Ecuadorian coast, and the most widespread coral bleaching ever recorded at that point. Hundreds of billions of dollars in economic damage. The 2015 to 2016 event pushed 2016 to become the hottest year on record at that time, erased harvests across multiple continents, and left more than 60 million people facing conditions of acute food insecurity. These were serious events, consequential events, events that tested governments and humanitarian systems and agricultural supply chains to their limits. But here is the thing that changes the entire calculation. Every one of those super El Niños happened on a cooler planet than the one we are living on right now. The baseline has shifted. That is the central fact around which everything else in this story orbits. The Earth today is approximately 1.3 degrees Celsius warmer than it was before industrialization. The 12-month period ending in early 2026 was the warmest 12-month period ever recorded in human history. Global ocean heat content, the total thermal energy stored in the upper 2 kilometers of seawater, reached a new all-time high in 2025, and according to measurements from the World Meteorological Organization, that rate of ocean warming has been accelerating. Over the last 2 decades, it has been increasing more than twice as quickly as during the late 20th century. More than 90% of the extra heat that greenhouse gas emissions trap on Earth ends up in the oceans, not in the atmosphere, not warming the surface in the way a thermometer measures. In the oceans, sitting there, building up, year after year. That stored heat is the loaded spring, and El Niño is the mechanism that releases it. Under normal conditions, an El Niño event borrows heat from the ocean and dumps it into the atmosphere. Sea surface temperatures climb. Global air temperatures follow. Then, when El Niño fades, the heat debt is repaid. Temperatures come back down. The ocean recharges. The cycle continues. The assumption embedded in that cycle, the assumption that has held for 10,000 years, is that the ocean has room to recharge to something close to what it started with. That after the heat is released, there is a stable baseline to return to. That assumption is now uncertain, because the ocean is not returning to the same baseline it had after the 1997 event or the 2015 event. It is returning to a baseline that is itself warmer than the previous baseline. Each recharge cycle starts from a higher floor. Each El Niño event, therefore, begins from a higher floor. And each release of heat into the atmosphere starts not from the historical average, but from something elevated above it, and then climbs higher still. Think of it not as a single wave, but as a wave riding on top of a tide that is itself rising. The wave is natural, the tide is not. And the question that matters, the question that the climate system has never had to answer before in the modern record, is what happens when a wave as large as a super El Niño crests on top of a tide, as high as the one we are currently sailing on. The warning signs began building months ago. In early 2026, the tropical Pacific returned to what meteorologists call an ENSO-neutral state after a weak La Niña that had briefly cooled parts of the ocean surface. At the surface, things looked unremarkable. By the standard measurements, nothing exceptional was happening. But the standard measurements look at the surface. What was happening below the surface was a different story. Ocean subsurface heat content, the thermal energy sitting in the water column below the surface layer, had been climbing for months and was sitting well above historical norms. Then, in the late winter and early spring of 2026, meteorologists began observing something that climate scientists recognize as one of the most reliable precursors to a strong El Niño event: bursts of westerly winds. Winds blowing from west to east, opposite to the normal trade wind direction, began moving across the tropical Pacific. These westerly wind bursts drive warm water eastward. They push it toward the South American coast. They suppress the upwelling that keeps the eastern Pacific cool, and they generate Kelvin waves. Those massive, subsurface pulses of warm water that travel thousands of miles before surfacing. Satellites caught one of these Kelvin waves in action. You can see it in the data, a bright thermal ridge pressing steadily across the Pacific, like the bow wave of something enormous moving just below the surface. In March of 2026, NOAA's Climate Prediction Center placed the probability of El Niño conditions emerging by summer at around 80%. Not certain, not unprecedented. A significant probability, but one that had been seen before. Then the European Center for Medium-Range Weather Forecasts released its updated projections for late 2026. The probability figure that came back from their ensemble models caused genuine alarm in the climate science community. 100%. A 100% probability of strong to super El Niño conditions developing by late autumn. The projected peak sea surface temperature anomaly in the Central Pacific, the number that would determine the event's intensity category, was 3 degrees Celsius above historical average, a level of ocean heat in that region that has not been recorded since 1877, 150 years ago. At this point, the comfortable explanation presents itself, and it is worth taking seriously because it is not wrong. El Niño has happened before, many times. It has happened on scales similar to what the models are now projecting. The 1997 event reached comparable ocean temperatures. The 2015 event was the strongest ever recorded at that time by the then current measurement standard. Both were survived. Both caused enormous damage, disrupted hundreds of millions of lives, and tested global systems in ways that revealed serious vulnerabilities. But the planet came through. La Niña followed. Ocean temperatures dropped. Agricultural systems recovered. The climate system reset. The comfortable reading of the current situation is that this is another strong event. Serious, costly, demanding of preparation. But ultimately another point on a cycle that has been turning for millennia. The cycle turns, it will turn back. What goes up in a Kelvin wave eventually comes back down. What heats the atmosphere during El Niño eventually transfers back to the ocean during La Niña. The system corrects. This reading is not unreasonable. It is supported by history. It is what climate scientists reach for when they want to communicate appropriate preparedness without inducing paralysis. And for the first 3 or 4 years after every previous super El Niño, this reading appeared to be correct. The temperatures peaked, the floods receded, the droughts broke. The coral began, slowly, painfully, partially, to recover. The global temperature anomaly that spiked during the event came back down when La Niña arrived. What no previous super El Niño had to reckon with was the level of background heat already accumulated in the ocean when the event began. What none of them had to contend with was the fact that the baseline had moved. What none of them occurred on top of was a planet that had already spent 12 consecutive months above the 1.5-degree warming threshold that the Paris Agreement identified as the upper limit of manageable change. The cycle will turn, but it may not turn back to where it started. There is a detail in the physics of the climate system that does not often make headlines. Because it is slow, and it is invisible, and it does not have an image attached to it. But it is arguably the most important number in the current situation. Ocean heat content lag. When greenhouse gas emissions trap additional heat in the Earth's atmosphere, that heat does not stay in the air. The oceans absorb the majority of it, slowly, over years and decades. What this means in practice is that the heat currently sitting in the ocean does not represent the impact of today's emissions. It represents the accumulated impact of emissions from decades past, finally, filtering down into the water column. The ocean, in other words, is not showing us the present. It is showing us the past, catching up. And the implication of that lag is deeply uncomfortable, even if every greenhouse gas emission on Earth stopped tomorrow. Every power plant, every vehicle, every industrial process, the heat already committed to the ocean would continue warming the water for years to come. The Kelvin waves currently pressing toward the South American coast contain heat that was captured years, possibly decades ago. The baseline that a super El Niño in 2026 is starting from reflects not just current warming, but all the warming already in the pipeline. The spring is already compressed. The wave is already moving. The floor is already higher than it has ever been. What this means for the event now developing is that the standard framework for understanding El Niño impact, the one built on 40 years of satellite observation and historical climate records, was calibrated to a different planet, a planet with lower ocean heat content, a lower temperature baseline, and more headroom above dangerous thresholds. That framework is being applied to conditions it was not designed to evaluate. The specific consequences of a super El Niño of the scale now being projected are not evenly distributed. They are not random. The same regions that were devastated in 1997 and 2015 face the same patterns, but amplified by the elevated baseline. For South and Southeast Asia, the primary risk is monsoon disruption. El Niño shifts the circulation patterns that drive the summer monsoon across the Indian subcontinent and Southeast Asia. A strong event weakens those patterns. Rainfall arrives late, or arrives below average, or fails to arrive at all in the periods when crops most need it. The 2015 event contributed to one of India's worst agricultural droughts in decades. The India Meteorological Department has already projected the 2026 summer monsoon at roughly 92% of its long-period average, the lowest in nearly 30 years. That shortfall, in a country where hundreds of millions of people depend on subsistence and small-scale farming, translates directly into food insecurity. Not just reduced harvests, food price inflation, supply chain disruption, rural economic stress that radiates outward. For the Amazon basin, the dynamic is different but equally severe. El Niño brings drought to the Amazon, already one of the most climatically stressed large ecosystems on Earth. Roughly 40% of the Amazon is already affected by some form of forest degradation, primarily from decades of deforestation. A super El Niño on top of that creates conditions for fire that are genuinely unprecedented. Previous super El Niño events have done something that should not be possible for a rainforest. They have converted large portions of the Amazon from a carbon sink, a system that absorbs CO2 from the atmosphere, into a carbon source, releasing stored carbon as trees die in the heat and drought. With the baseline already elevated, the threshold for that conversion is closer than it has ever been. For East Africa, Kenya, Somalia, Ethiopia, El Niño typically brings the opposite problem. Not drought, but catastrophic flooding. Above average rainfall that sounds like relief until you see what it does on the ground. The 2023 to 2024 El Niño, which was not even a super event, displaced hundreds of thousands of people across the region in flooding that overwhelmed infrastructure that had never been designed for that volume of water. A super event in 2026, on a continent with rapidly growing populations and limited adaptive capacity, would generate a humanitarian scale of displacement that existing international systems are not currently resourced to manage. For the ocean itself, specifically, the coral reef systems that form the biological foundation of tropical marine ecosystems, the threat arrives from a direction that most people never consider. Coral bleaching is triggered by water temperatures. Coral organisms expel the symbiotic algae that give them both their color and their food source when water temperatures exceed a threshold for long enough. Bleaching does not immediately kill coral, but repeated bleaching events with insufficient recovery time between them do. The 2015 Super El Niño triggered the most extensive global coral bleaching event ever recorded at that point. If 2026 matches or exceeds it on a higher baseline ocean temperature, the recovery time available to reefs between this event and whatever follows is shrinking toward zero. The United Nations World Food Program has estimated that the number of people facing acute food insecurity globally could, under a Super El Niño scenario, approach levels not seen since the early years of the Russia-Ukraine conflict in 2022. Somewhere in the range of 300 million people simultaneously under severe food stress, not as a consequence of a single crop failure in a single country, as the aggregate effect of simultaneous disruption across multiple major food-producing regions. And underneath all of this, underneath the floods and droughts and fire seasons and coral bleaching and monsoon failures, there is the global temperature number. El Niño events consistently produce the warmest years on record. The 1997 to 1998 event made 1998 the hottest year at that time. The 2015 to 2016 event made 2016 the hottest year at that time. The pattern is reliable. El Niño releases ocean heat into the atmosphere. Global average temperatures rise during the event's peak, typically lagging the peak ocean temperature by several months. Then, when La Niña follows, temperatures drop back. The critical issue for the 2026 event is not the peak. It is the floor that the peak is starting from. James Hansen's team at Columbia University has projected that global temperatures could reach 1.7 degrees Celsius above pre-industrial levels by 2027. That would not be a permanent crossing of the 1.5 degree threshold. Temperatures would likely drop back when La Niña conditions follow, but it would mean that for a period of 1 to 2 years, a meaningful proportion of the human population would experience what climate science refers to as a 1.5 degree world, not as a projection, not as a scenario in a model, but as the actual weather outside their windows. The distinction matters. There is a difference between a climate scenario that predicts 1.5 degrees of warming by the 2040s and a summer in 2027 where the global thermometer reads 1.7. The first is abstract. The second is what a farmer in Maharashtra experiences when the monsoon fails for the second year running. It is what a fishing community in the Galapagos experiences when the ocean currents that support their livelihood have shifted beyond the range of their knowledge. It is what a city in the Pacific Northwest experiences when a wildfire season's 3 weeks earlier than any season in living memory. The 1.5 degree number from the Paris Agreement was never meant to describe a safe threshold crossed briefly and then retreated from. It was meant to describe the upper limit of a warming trajectory that humanity could manage without cascading irreversible consequences. A single year above that number does not mean the trajectory has been crossed permanently, but it means that the buffer between the current trajectory and permanent exceedance is now thin enough that a single natural climate event can temporarily eliminate it. That is a different kind of vulnerability than any previous generation of climate scientists was working with. There is something in the physics of this situation that warrants more attention than it typically receives in public discussion. The La Niña that will follow this El Niño. And La Niña always follows El Niño. that is not in dispute, will cool the ocean surface. Global temperatures will drop. The headline numbers will improve. Climate scientists will point to the return toward baseline as evidence that the system is still functioning, still self-correcting, still operating within the range of historical variability. And all of that will be true. What will also be true, and much harder to measure, is the state of the systems that were stressed during the Super El Niño and were given insufficient time to recover before the next event arrives. Coral reefs that bleached in 2027 will not have fully recovered by the time the next El Niño cycle begins. Amazon forest tracts that burned in 2026 will not have regenerated before the next drought. Glaciers that lost mass during the heat peak will not rebuild that mass during a single La Niña winter. Monsoon patterns that were disrupted will return to something closer to normal. But agricultural communities that lost a year or two of harvests will still be working through that debt when the next disruption arrives. The question is not whether the climate system will self-correct. It will. It always has. The question is whether the self-correction is fast enough to matter. The cycle is still turning, but the damage accumulates between turns. And this is where the standard framework for thinking about El Niño, built on the assumption that the system resets cleanly between events, begins to strain against the evidence. Return to the Kelvin wave, that warm, subsurface pulse pressing steadily toward the South American coast. In every previous Super El Niño, that wave was carrying heat that had accumulated during a La Niña cooling period, starting from an ocean baseline that was itself cooler than the historical average. The wave was anomalous relative to the background. It was a spike above a stable mean. What satellite measurements are now showing is something subtly but fundamentally different. The Kelvin wave forming in 2026 is anomalous relative to a background that is already elevated. The ocean is not at its historical mean, and then spiking upward. The ocean is above its historical mean, and the wave is spiking above that. The anomaly is sitting on top of another anomaly. The difference is not just quantitative, it is structural. When you run an El Niño event from an elevated baseline, the heat that gets transferred to the atmosphere is not just the heat in the wave. It is the accumulated heat of the wave, plus the heat of the elevated baseline. The atmosphere receives more energy than the historical record suggests. Regional temperature peaks go higher. Drought conditions persist long before the atmospheric circulation can push rainfall back into drought-affected zones. Flooding events receive more moisture from a warmer ocean, because warm oceans evaporate faster, loading the atmosphere with more water vapor before the rains arrive. The feedback loops are the same as they have always been. The starting conditions are not. And the starting conditions matter enormously when you are operating close to thresholds. A fire weather threshold that was not quite reached during the 2015 event may be crossed during the 2026 event. Not because the El Niño is necessarily stronger, but because the baseline was already closer to the line. A monsoon weakening that would have reduced rainfall by 15% in 2015 may reduce it by 25% in 2026. Not because El Niño has changed, but because the atmospheric circulation it disrupts is operating in a warmer, more energetic system. Mechanisms are still running, but they are running hotter. Here is the deeper problem. The models that forecast Niño impacts, the ones that governments use for disaster preparedness, that agricultural ministries use for crop insurance, that hydrologists use for reservoir management, were calibrated on the historical record. They were trained on data from previous El Niño events. They encode the statistical relationships between Pacific Sea surface temperatures and rainfall in India, or temperature anomalies in the Pacific Northwest, or drought probability in the Amazon, that were observed over the last 40 to 60 years of satellite-era data. Those statistical relationships were real. They held through multiple El Niño cycles. They were validated against observations. They are the best available tools for forecasting what a strong El Niño will do. But they were derived from a different climatic state than the one now unfolding, and the degree to which they remain accurate predictors when applied to a super El Niño starting from an elevated baseline is genuinely uncertain. Not wrong necessarily, not useless, but uncertain in ways that the models themselves cannot fully quantify, because there is no historical precedent to train against. The climate models are being extrapolated beyond their validation range. This is not a criticism of the scientists using them. It is a structural feature of the situation. The current event is, in a specific and important sense, outside the historical record. The ocean is warmer than it has ever been during an El Niño precursor period. The atmospheric baseline is higher than it has ever been entering a potential super event. The confidence intervals around impact projections, the error bars that represent genuine scientific uncertainty, are wider than they would be for a similar strength event occurring in a cooler baseline state. The forecasters are working at the edge of what their instruments were built to measure. What would it mean if the impacts of this event significantly exceeded historical precedent, not catastrophically, not civilization ending, but meaningfully, systematically, across multiple domains simultaneously? If the Amazon fires in 2026 release more carbon than in any previous fire season, that is not just an ecological tragedy. It is a feedback. The carbon enters the atmosphere. It increases the concentration of greenhouse gases. It adds to the warming that is already committed. It raises the baseline further. The next El Niño event, 2 to 7 years from now, will start from a baseline that is higher still. If the monsoon drives food price inflation that exceeds the capacity of governments and international food systems to manage, that creates instability that reaches into supply chains and political systems far from the Pacific. El Niño has been linked repeatedly across historical research to elevated risk of political instability and conflict in countries heavily dependent on rain-fed agriculture. The mechanism is not mysterious. Food insecurity destabilizes governments. Destabilized governments make decisions with consequences that outlast the El Niño that triggered the original stress. If coral bleaching in 2026 and 2027 reduces the reef coverage that supports the fisheries that feed hundreds of millions of people across the Indo-Pacific, those people must find protein from other sources. That pressure on agricultural systems adds to the pressure already created by the monsoon failures and the Amazon drought. Multiple stresses arrive simultaneously. They compete for the same adaptive capacity, and the recovery time available before the next event ever is shorter than it has ever been. These are not worst-case scenarios. They are extensions of documented historical patterns, applied to conditions that are quantifiably more extreme than the conditions those patterns were observed under. The risk is not that any single one of these outcomes overwhelms the system. The risk is that several of them arrive together on a global system that has been running under compounding stress for years, and that the recovery time available between this event and the next El Niño cycle is insufficient for the most fragile systems to stabilize. The climate system will correct. It always does. But the threshold for what the correction leaves intact may be shifting. There is something that does not receive adequate attention in the public discussion of El Niño events. The cycle is not just a climate phenomenon. It is a memory system. Every time El Niño stresses a reef, that reef enters the next La Niña recovery period in a weakened state. Every time a monsoon failure reduces soil moisture, that deficit carries forward into the following agricultural season. Every time a fire season burns through a section of the Amazon, that land enters the next drought period without the canopy that previously provided shade and moisture retention. The damage compounds. The system's capacity to absorb the next event is smaller than its capacity to absorb the last one. This is not a new observation. Ecologists and climate scientists have been documenting this compounding damage for decades. What is new is the rate. What is new is that the events are arriving faster and starting from higher baselines and hitting systems that have had less recovery time than the systems that faced previous events. The Kelvin wave now crossing the Pacific is, in one sense, exactly what it has always been. Warm water moving east, physics unfolding exactly as it has for 10,000 years. But the ocean it is moving through is not the ocean it has always moved through. And the continents it is about to reorganize weather across are not the same continents. They are the same geography. They are not the same systems. At some point in the next several months, the wave will arrive. Sea surface temperatures in the eastern Pacific will climb. The trade winds will continue to weaken. Tropical convection will shift eastward. The atmospheric circulation patterns that determine where it rains and where it does not will begin to move. The consequences is that climate models, calibrated to historical precedent, but now operating at the edge of their range, are projecting, will begin to materialize or not materialize in ways that will be visible not in forecast numbers but in the actual weather outside actual windows. The forecasters will keep updating their models. The probability estimates will narrow. At some point, the uncertainty range will collapse into a specific event with specific outcomes in specific places. What we will learn from those outcomes is something that no previous El Niño event could have taught us. We will learn whether the historical statistical relationships between the Pacific Ocean temperatures and continental weather patterns hold when the baseline has shifted as far as it has shifted. We will learn whether the damage accumulation from previous events, the weakened reefs, the stressed forests, the agricultural systems that never fully recovered, places a different ceiling on how much stress the system can absorb and still return to something recognizably similar to what it was. We will learn, in other words, something fundamental about the resilience of the climate system at its current state. Not the climate system of the 20th century. This one. The one we actually have. That knowledge, when it arrives, will not come from models or forecasts. It will arrive as rain, or the absence of rain, as fire or the absence of fire, as a harvest, or the failure of one. It is an experiment. We did not choose to run it. It is running regardless. The cycle will continue after this event, as it has for 10,000 years. La Niña will follow. Ocean temperatures in the Central Pacific will drop. Global average temperatures will likely decline from wherever they peak. The Pacific will recharge. But the recharge will bring the ocean back to a baseline that is itself higher than the baseline that existed before the event began. The floor will be where it is, not where it was. And somewhere in the water column, not visible from the surface, not audible from the shore, not measurable without instruments calibrated to detect the difference between now and 30 years ago, another Kelvin wave will be forming. 2 years from now, or 5, or 7, not a question of if, never a question of if. The wave is always forming. That is the nature of the cycle. The question that this event will not answer. The question that may not be answerable from inside the system that is running the experiment is whether the cycle that has been turning for 10,000 years is still the same cycle it was, or whether it has become something else, something that still moves in the same patterns, still follows the same physics, still builds and releases on the same rhythm, but builds higher each time and releases into less.